Why do I have a box here? I don't know. Oh, okay. So here is another topic. So previously, and please let me have some water. So previously we said that we can have linear and curvilinear relationships between two variables, right? That's really the most simple scenario that we can possibly envision. Um, we call those scenarios bivariate, correlations. So bivariate, variate, right? V-A-R-I-A-T-E. Bi means two, right? Variate simply means variables. So relationships between two variables. But in actually many cases, we can just focus on two variables for reasons that we'll discuss very soon. Um, in many cases, we have three, we have four, and sometimes we can even have hundreds of variables to consider at the same time. So if that happens, what can we do, right? Can we still describe the relationships between all those variables? Well, the answer is of course we can, but to do that, we need to understand some concepts. So let's, for the purpose of this class, consider a scenario that has three instead of two variables. And that will be our upper limit, so to speak, for this class. Because once you understand a third variable situation or a three variable situation, you can easily extend the same idea, to situations that have more than three variables. So a three variable situation is the foundation to understand multivariate relationships. Okay? All right, so there are two situations that we will discuss. The first situation is when the third variable is a confounding variable, or simply a confound. The second situation that involves a third variable is when that third variable is a moderator or a moderating variable. Okay? So depending on what the third variable is, a confound or a moderator, um, the nature of the relationships will be vastly different. Okay? So let's go through them one by one. So first of all, let's talk about a confound. So let me just first of all give you the definition of a confound or a confounding variable. So this definition essentially tells us how to identify a confound, right? That means when we see a situation that has three variables, how do we know that the third variable is a confound? So the first criterion is that the confounding variable must correlate with both the predictor and the outcome variables. So let's start with the two variable situation. Here we have variable x, and then we have variable y, and this arrow pointing from x to y means x predicts y, right? We use x to predict or to explain y. Now, we have a third variable then. We add a variable z to the situation. So you might ask, without knowing, what a confound means, You ask, okay, so what does z do here, right? How would z impact the correlation between x and y? Well, it turns out that the first thing we'll examine is whether z correlates with x and correlates with y. So in this case, let's assume that z does correlate with y and, z correlates with both x and y. Okay, so that's why we have arrows pointing from z to x and arrows pointing from z to y. The second criterion of identifying a variable as a confound is when the correlations between the confound and the predictor and outcome variables are statistically controlled for. We'll explain what this means, right? But for now, just, learn this by heart. The original correlation, that is, the correlation between the predictor and outcome variables, will disappear. Once the third variable fulfills all three criteria, we'll call this third variable a confounding variable. Let me repeat, right? If we can establish that, first of all, a third variable correlates with both the predictor and outcome variables, and once we can control these two correlations between the confound and predictor, between the confound and outcome variables, right? Two correlations. Once these two correlations are statistically removed, that will be another way to express the same idea. Then the original correlation that existed between the predictor variable and the outcome variable will become zero. When that happens, we'll say that the third variable is a confound. So graphically, it looks like this, right? So we have two variables, x predicting y, and before we're adding z to the scenario, there's a correlation between x and y. It can be negative, it can be positive, it can be linear, it can be curvilinear, doesn't matter, right? So if variable z is a confound, first of all, z must correlate with both x and y, right? And once we statistically control for this correlation and this correlation, the original correlation between x and y, here designated by a solid line, is gone. Now it's designated by a dashed line, meaning the correlation between x and y disappears. And when that happens, we say that the original correlation between x and y is spurious, or spurious, depending on how you pronounce the word. It's, well, spurious, okay? Or it's fake. It's not true. It's not reliable. There are many ways to express the same idea, but that's what a spurious correlation means. A spurious correlation means once a third variable, the effect of the third variable is controlled for, the original correlation is gone. When that happens, that correlation, we call it spurious. Okay? And variable z is a confound, or a confounding variable. Another way to think about it is x and y are related, or appears to be related to each other, simply because a common factor z. Z, the existence of z, is the reason why x and y are related to each other, once we take out the effect of z, that is, once we statistically control for this correlation and this correlation, there will be no more correlation between x and y. And that's why we call z a confound. It's actually a good thing, right? Confound sounds negative, but it's actually a good thing because now we discovered the true reason, the true cause of this correlation, right? It's good. It's actually a very valuable very valuable piece of information to have. So let's look at some examples. Some very famous examples that involves confounds. So it turns out that, for example, there is a very strong correlation between a person's size of shoe size, and that person's math skill, how good the person is at math, solving mathematical problems. And this correlation is positive, right? A line is arranged as such. So that means as a person wears larger shoes or bigger shoes, the person will be better at solving mathematical problems. That's correlation, and that correlation does exist. The question is, of course, that doesn't make much sense at all, right? There's very this correlation is very counterintuitive. How could a person's shoe size correlate with the person's math ability? So that poses a question for researchers to explain, right? To explain this unreasonable correlation, to explain this correlation that doesn't make much sense. So what's your thought? Why do you think that shoe size would correlate with math skill at all? This correlation does exist, but our job is to figure out why this correlation, which should not exist at all, is actually observed. Another way to phrase this question is there a third variable whose existence cause this fake or spurious correlation to exist? Is there a third variable because of which shoe size and math skill become associated with each other? Okay, I'll give you a few seconds to consider. And you can pause before I announce the answer. The answer, if you're ready, is age. I think that makes a lot of sense, right? As you become older, you wear larger shoes. As you become older, your brain actually develops better and you'll be better at solving math problems. I bet that now you will be very good at solving math problems that you encountered in the first grade, right? You're better. You become better as you grow older. So that means what really correlates with math skill is actually a person's age. But just so happens that as you grow older, you will also become your feet will also become larger, and as a result, you wear bigger shoes. So that's the reason that we can observe a correlation between shoe size and math skill. The only reason that these two variables, which should not correlate with each other, correlate with each other is because they're both related to a third variable, which is age. Make sense? I hope it does. Well, let's look at another example. Once upon a time, researchers discovered another surprising correlation, and that correlation is between murder rates and the sales of ice cream. They discovered that as in a city, ice cream sold better, murder rates increased. Why would that happen? As if we sell more ice creams, we're producing more murders, more horrible crimes. That doesn't sound very reasonable, and this correlation again is very counterintuitive. It can't be true, right? How would these two variables that are very, very different, well, I shouldn't say that, well, but you know what I mean, right? So these two variables should not be related to each other, and they're not. And now we observe this spurious correlation again because of a certain third variable. This third variable, as in the previous example, must correlate with both murder rates and ice cream. And it should provide a good explanation why these two would appear to be related. Okay? So again, I'll give you a few seconds to consider what could this third variable be. Right? Okay? You can pause, but if you're ready, the third variable, as some of you or all of you might have guessed, is heat. It makes sense because as weather becomes warmer, definitely you will sell more ice cream. But at the same time, it turns out once the weather becomes warmer, people will become more aggressive. And the result of more aggressiveness is increased murder rates. So again, right, ice cream sales related to murder rates simply because both these two variables are related to heat. As weather becomes warmer, you sell more ice cream. As weather becomes warmer, you observe more murder cases. And as a result, it appears that ice cream sales will increase along with murder rates. But again, this correlation is spurious. It's not real, it's fake. It's fake because this correlation exists only because they're both related to the third variable, which is heat in this case. Okay? All right. So let's, repeat our definition for confounding variables. That is, if, the two variables x and y, they have a spurious correlation, that means this correlation between x and y will be gone once the correlation between the confounded x, heat and ice cream sales, for example, and the correlation between confounded y, heat and murder rates, for example, when these two correlations, correlation 1, correlation 2, when these two correlations are statistically controlled for, the original correlation between x and y will disappear. Right? And that's when we call this correlation between x and y is spurious. But the question, of course, is what does it mean to statistically control for a correlation in the context of identifying confounds? Okay? Well, to statistically control for the effect of a confound variable z, it is to examine, I'll just read this verbatim, the correlation between the original two variables x and y at every value or every level of z. I hope this makes sense because z is a variable, right? It's a confounding variable, and we said in the previous lecture that the definition of a variable is it can take different values. Sometimes we'll call those values levels, right? So that's why we say, why this phrase, every value of z should make sense, right? So when we're examining the correlation between x and y at every level or every value of z, if the correlation between x and y still holds, then the xy correlation is real. It's not fake. It's not spurious. However, if the correlation between x and y, when examined at every value of z, is reduced to 0, then the correlation between x and y is spurious. Okay? This will sound, I'm sure, quite foreign to most of you. That's understandable because it is not some kind of idea that we talk about with our friends at a bar, right? We don't discuss, a correlation is spurious when we're drinking Heineken, but that's exactly why we need this class to introduce to you this very important idea in analyzing data for all kinds of purposes. You can go to marketing, you can go to education, go to PR, you can go to law firm. It is guaranteed that you will encounter some kind of relationship like this, and you should be able to understand the idea behind it. Okay? So this is the definition of statistically controlling for the effect of a confound. That is to examine the original correlation, the correlation to be explained, the correlation that we would like to demonstrate as spurious at every value of z. If at every value of z, the correlation under examination still holds, then the correlation is real. But if the correlation to be examined or under investigation, it's reduced to 0 at certain value of z, then this correlation between x and y is not real, it's spurious. Let's look at an example. So we'll use this example between, the correlation, spurious correlation between math skill and shoe size as a demonstration. So here we have the two variables, shoe size and math skill, right? And we can plot all the data points. So we use triangle to represent math skill and shoe size, square to represent shoe size. So if we look at these data points, they do appear to be a very strong positive correlation, right? So if we draw a line through this data points, we see a pretty, okay, this is not perfectly straight, but you know what I mean here. It's a linear relationship, right? So now our job is, since we know that this correlation is spurious, we need to explain why it is spurious. And fortunately, we have the tool to our use, and that's the definition that we discussed just now. That is, once we introduce a third variable, age in this case, and once we start to examine the correlation between math skill and shoe size at every level of age, we will see whether this positive correlation will still exist or be gone. Okay? So to do that, we need to introduce the third variable, age, into this graph. Okay, I do have a line here. Anyway. Okay, so what I did here is I rearranged this coordinate so that I keep math skill here, but I replace shoe size with age at the x-axis because our goal is to examine whether at each level of age of 10, age of 20, age of 30, age of 40, age of 50, right? That's at every level or every value of age, whether the correlation between math skill, triangles, and shoe size, yellow squares, whether the correlation between these data points still is positive. Okay? If the correlation between math skill and shoe size at each level of age is still positive, then the correlation between these two guys is real. But if at every level of age the correlation between shoe size and math skill is gone, then the correlation between math skill and shoe size will be spurious. So to facilitate our examination, I group all those data points and roughly at each level of age. We can definitely be more concise or precise, so to speak, but I believe that this crude categorization should suffice our purpose, right? So these data points correspond to the math skill level of math skill and shoe size at age 50. These will be math skill and shoe size at age 40, at age 30, 20, and 10. So roughly, actually, well, if for illustration purposes, right, it turns out that despite that there's overall trend of positive correlation, right? So if we ignore the groupings, if we only focus on the overall trend, it does appear that there's a positive correlation between math skill and shoe size. But once we focus on the correlation between math skill and shoe size at each level of age, all of a sudden the positive correlation is not there anymore. What really happens is a flat line, flat line, flat line, flat line. In other words, there's no real pattern that can best describe math skill and shoe size at each level of age. And previously, if we recall, we say that once we say that the two variables have no correlations, we can use a flat line to represent the zero correlation, right? Here we see we have flat lines between math skill and shoe size at each level of age. That means there's actually no correlation between math skill and shoe size at every value of age. That's what we mean by statistically controlling for or removing the effect of age. And once we do that, the correlation between math skill and shoe size is gone. It's no longer a positive correlation that they appear to show. In actuality, there's no correlation between math skill and shoe size. Okay? So dashed line again represents a spurious correlation. That's when we ignore age. So there's overall trend that appears to be positive, but once we take age into consideration, that is, we examine the correlation between math skill and shoe size at each level of age, it's actually zero correlations, right? Zero correlation, zero correlation, zero correlation, zero correlation. Okay, that's what we mean by identifying confounding correlations. Okay,